In this reaction, we're going to use calorimetry. Now we have a calorimetry equation, which is Q equals mc delta T, where Q is the energy absorbed in joules, M is the mass, C sub S is the specific heat capacity in joules per gram degree Celsius, or sometimes calories per gram degree Celsius. So this is the amount of energy it takes to raise the temperature of 1 gram of our substance by 1 degree Celsius. And then delta T is our temperature change. Now, note that here that Q, the heat absorbed, and delta T, the temperature change, are signed. M and C sub S are both always going to be positive, so we know the sign there is positive, but delta T and Q can either be positive or negative. Now, because these two are always positive, if delta T is positive, that means Q is also positive. What that means is the temperature is going up because heat has been absorbed by our system. Energy is flowing into the system, and so the temperature is going up. On the other hand, if the sign on delta T is negative, then the temperature is dropping as heat is being released by our system. Heat is going out of our system. And so the signs here on Q and delta T tell us the direction that energy is flowing, either in the case of positive values, or out in the case of negative values. We're also going to use Hess's law. Now, Hess's law looks something like this, where if we have an initial state, we would generally call these the reactants, and some final state, we would generally call these the products. It doesn't matter whether we get from the initial state to the final state in one step, like we do here in reaction 3, the red path, or if we take multiple steps, like going through some intermediate state or multiple intermediate states, like we have here with the green path. If we start and end at the same places, the energy change of path 1, the green path, of reaction 1, enthalpy change 1, plus enthalpy change 2, must be the same as the energy change along any other path between these two states, so between the red path. So the sum of enthalpy change 1 plus enthalpy change 2 must be equal to enthalpy change 3. We are also going to use a digital device to collect data for us, the LabQuest. So the LabQuest has a power button on the top left here. It has a power adapter that plugs in on the right side. Behind that is a stylus that you can use to touch various places on the screen. If you're like me and have larger fingers, it can be very difficult to touch accurately and push the buttons without fat fingering and pushing somewhere else. Down the left side, you have a USB port, and then there are 3 analog probe ports. On the top, there is a digital port behind this rubber door. We're not going to be using the digital ports in this experiment, but we will in later experiments. We're going to use the ports down this left side to plug in the temperature probe. Let me plug that in, and you should see fairly quickly the temperature should show up on the LabQuest in this red meter tab. Now, the temperature probe has this black portion, which has a small computer chip in it. We want to make sure that that black portion does not get wet. And then there is this stainless steel portion. And down at the end of this stainless steel portion is what's called a thermocouple. And that thermocouple changes its voltage depending on the temperature. So if I grab it, you should be able to see the temperature changing on the LabQuest. The LabQuest then measures the voltage in that temperature probe. Now, that voltage change is relatively small for small temperature changes around room temperature. And this means that there tends to be a fairly significant noise on top of that signal. And so if we plot what we generally see with temperature on the vertical axis and time on the horizontal axis, what we'd like to see is a nice smooth line, whether it be a flat line if you just are measuring, say, room temperature, or if it has a peak in it. We don't generally see that. Instead, what we tend to see when we're measuring just a constant temperature is some random noise in there. Now, you should be able to recognize that those variations are random noise down to the electronics in the device and noise in the voltage signal that it's seeing. What generally we would want to do then is take an average over some range, average all of that rather than just picking any one value in there. And by averaging those values, we should be able to eliminate the random noise that's higher than average and lower than average. It should largely cancel out over a sufficiently wide temperature range. So be aware, if instead of having a smooth curve like this, or a flat curve like that, rather, if you have, say, an initial temperature and then it goes up to some maximum and then starts to come down again, you'd want to average out over what looks like pretty darn close to the maximum temperature, but not necessarily the maximum temperature if that point is the result of noise. If you have some noise on top of the signal, you don't necessarily want to pick that top value because it may be higher than the true maximum temperature attained by the temperature probe. Now to start collecting data, you'll push this green icon down here in the bottom left to start collecting data. And that will collect some data over time. And I'll allow that to go for a while, and we'll come back to it. Okay, so I've collected some data for a while. I'm going to push the stop button, which is in the same place that the start button was in, down in the bottom left. And the LabQuest should automatically scale the data. If it doesn't, we can come up here to the graph and click on Graph, Auto Scale Once, and that will auto scale it for us. You can see that there's some noise in that data. So suppose I want to find the average temperature over some range. I can click and drag across some temperature range, click on Analyze, click on Statistics, and then click Temperature, because I want to analyze the temperature data. And then over here on the right, it shows up with the statistics. In this case, it shows that the mean, the average temperature, is 22.6 degrees Celsius. So let's talk about safety. The hydrochloric acid is severely corrosive to human tissue. The potassium hydroxide that we'll use is also severely corrosive to human tissue. The ammonium chloride is both a toxin and an irritant to humans. The ammonia, the NH3, is toxic and corrosive to human tissue. It also smells very strongly, so you want to keep it under the mini hood. And when you react the ammonium chloride with potassium hydroxide, you're going to produce ammonia, and so you're going to want to keep this under the mini hood when you perform that reaction to minimize the fumes coming out. Now in this experiment, we're going to use potassium hydroxide rather than the sodium hydroxide that the procedure calls for. The chemistry is identical, except that we'll have potassium ions in place of sodium ions. In addition, when the ammonia is dissolved into water, it reacts to form ammonium hydroxide, NH4OH. And this means that the bottles that you see in the lab will be labeled as ammonium hydroxide rather than as ammonia, rather than as NH3. At your lab station, you have this mini hood where if we bend down, you can see there is this gap here. If we open this sliding piece of wood, we now have quite a good bit of air that is being exhausted up through this pipe. This is the pipe that is above the sink in the lab. And so this space acts as a mini hood under which you can keep fumes relatively contained as they'll be exhausted up through that vent.